Hey everyone, in this next page we're going to be focusing on a special type of condensation called an intramolecular condensation. Alright guys, so it gets a little bit more complicated, right? So dicarbonyl compounds have the ability to self-condensate through cyclization if it will generate a 5 or 6-membered ring, okay? Here's the deal. Any ring below 5 members, 4, 3, way too unstable to cyclize on its own, okay? You're going to need to put a lot of energy into that system to make it happen. So in order for these reactions to be favorable, we're going to try to make 5 and 6-membered rings, okay? That's actually going to be a theme later on when we talk about other reactions that condensation products can undergo, okay? So here I've got this diketone, right? Now this could happen to diesters, diketones, whatever, dialdehydes. The biggest point here is that when you make your enolate, you want to make your enolate in a place where if you attack the carbonyl, you'll make either a 5 or a 6-membered ring. So let me ask you a question. I've actually got 4 different positions that could make enolates here. I've got position 1, position 2, position 3, and position 4. Okay? Now, you guys understand that 3 and 4 are the same thing as 1 and 2, so I'm going to erase them because that's just distracting me. So I just have a choice between, do I put the enolate on carbon 1 or on carbon 2? They both have alpha hydrogens, so I could definitely get enolates there. The question is, the real way that you decide this is you decide by the ring that you could make after you cyclize. Okay? So let's look at, for example, enolate 2. If I were to put my enolate on carbon 2, then it would attack this carbonyl here. Okay? How big would that ensuing ring be? Well, this being my nucleophile always gets the first carbon in the count. So this would be 1, 2, 3, 4. Okay? You always count from nucleophile to electrophile. Is that big enough? No way. Let's talk about 1. So if I were to make it on 1, it can't attack that one. That's way too close. It would attack this carbonyl. So then let's count. Let's see if it's the right size. 1, 2, 3, 4, 5. Guys, that is a lot better. That's a 6-carbon chain that is going to connect between the 1 and the 6, making a 6-membered ring. Okay? So the NaOET is going to specifically make an enolate here so that it can cyclize on its own. Okay? Now, the mechanism is just going to be what you expect for any aldol reaction. You would kick up the electrons to the to the O, and then it would protonate. Okay? So what we could do here is, what I like to do is, if we already know it's going to be a 6-membered ring, let's just draw a 6-membered ring. And then let's just add the groups. Okay? Now, from lots of years of experience, I know that it's actually going to be easiest to number this ring if I start at, I guess, the top left corner, and I work my way around counterclockwise. So 1, 2, 3, 4, 5, 6. Literally, guys, this is just me trying to make it look as pretty as possible. You could have numbered it however you want. As long as your numbers are in order, it doesn't matter, okay? The only thing you can't do is like 1, 3, 5, 7, or whatever, okay? So, what am I missing? What groups do I need? Okay? So, it looks like I'm missing a ketone on 2. So I'm going to put that there. What else am I missing? It looks like I'm missing some stuff on 6. What am I missing on 6? Could you guys tell me exactly? Think about it. Think about exactly what's not on this chain, on this ring. I'm missing an OH, right? Because we said that it's going to protonate. Am I missing anything else? I'm also missing a methyl, right? Because look, this methyl was not part of the ring. It's just extra. So there we go. Now we have it drawn correctly. This is called what? What's the name of this product? This is our beta hydroxy carbonyl. You're getting professional at this point, okay? But what do we know about beta hydroxycarbonyls? They love to dehydrate, right? So we're going to dehydrate this bad boy. And we're going to dehydrate between the alpha and the beta. So what this is going to make as a final answer is I'm going to get what we call a cyclic enone. And guys, this is going to be highly favored because that's really stable, okay? So you're going to get a cyclic enone, and that's what you get when you have basically an intramolecular reaction. That's an aldol. This would be specifically an intramolecular aldol, right? You might say, Johnny, how do you know it was aldol? Because it's ketones or aldehydes, okay? And you're going to get a cyclic enone, okay? So in the next video, I'm going to show you what happens for intramolecular condensations of esters.